So this picture we've developed with hydrogen also applies as we continue down the periodic table, and for now we'll look at homonuclear diatomic molecules where we have the same two atoms. So if we look at something at, say, helium dimer, He2, now this is not going to be obviously a molecule, and what we can think about in the sort of diagrams we start to draw are sort of a shorthand notation we use is we take, we have one helium atom that has its 1s electrons, another helium atom that has its 1s electrons. Let me get my notation correct here. So this is, helium atom 1, helium atom 2. And we saw that these atomic orbitals, which in helium these are both full are going to combine to form our molecular orbitals. And the way we sort of diagram this is we show that we have one orbital that's lower in energy. This is our sigma bonding orbital. So we'll call it sigma B. And we have our one orbital, our anti-bonding orbital, sigma A, or sometimes also written as sigma star, that is higher in energy. And this is the orbital where the electron density is lower between the two nuclei and the energy is higher than our separate electrons. And if we fill in our electrons like we would for an atom, we would put in 2 electrons into the bonding orbital, and our other 2 electrons go into the anti-bonding orbital. And overall, we get that helium dimer does not form a bond because we don't have a net bonding effect between the two atoms because the electrons are in both a bonding and an anti-bonding orbital. Now this is a very, first order approximation to this. Helium dimer can form, but is a very, very weak bond between the molecules. And it's not even really a covalent bond. It's more of a sort of van der Waals sort of interaction. So that's sort of the next step we can take looking at helium dimer. And so we can keep going with this, right? So helium dimer, let's go to lithium next. Right, so our next atom down the periodic table. So now we're going to have an extra electron shell, right? We have our 2s electrons. All right, and so we'll have that for both of our lithium atoms. And the same thing will happen with the 2s orbitals as happens with the 1s orbitals. And what we'll see with these atomic orbitals, these linear combinations, is that only orbitals with similar energies will add and subtract. So a 1s orbital on a lithium atom is much lower in energy than a 2s orbital, and so the 1s orbitals will interact and form molecular orbitals, and the 2s orbitals will interact and form molecular orbitals. But you won't have a 2s and 1s orbital on lithium combining to form molecular orbitals. With similar energies will combine. And our same rule applies however many atomic orbitals go in, that's how many molecular orbitals we get out. So for our 1s electrons down here, we'll have 1, 2 orbitals that form. We have a sigma and sigma star orbital. And in lithium, these are full. And so overall, these core electrons don't really contribute to the bonding. And in fact, really, these electrons kind of just stay on their parent atoms. So, we write this as a molecular orbital, but in reality, it's more like the 1s electrons just stay attached to their respective nuclei. Our valence electrons is where the interesting stuff happens. So mostly we'll actually kind of ignore this 1s orbital stuff down here because it's really, as you already know, the valence electrons are what dictates bonding in molecules. Right, so our 2s electrons are going to behave similar to our 1s electrons, and they'll form a bonding and anti-bonding sigma orbital. And with lithium, we have 1 electron in each of these. And so lithium dimer forms a bond. Now, the next thing we need to do is define, how strong is this bond? And we introduced the idea of bond order, something that you're familiar with, like a single bond, double bond, with a slightly different definition here. All right, so the bond order is given by the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. Right, so basically you're looking at what are the net number of electrons in bonding orbitals, and antibonding orbitals count against your amount of bonding in your molecule, and then we divide this by 2. So if we come back up to our lithium dimer, everything down here in the 1s, down here, we have our bonding and antibonding electrons kind of cancel each other out, so they don't really contribute, and that's why I said we ignore that. And look at the valence, and we see we have 2 electrons in a bonding orbital. So our bond order is 2 electrons minus 0 electrons in an antibonding orbital divided by 2. And so we say this is a bond order of 1. This is a single bond. So lithium dimer forms a single bond. And lithium dimer is a molecule you can actually make. It's not something you can buy on a shelf, but if you get 2 lithium atoms in the gas phase to encounter each other, they'll form a bond and they'll form a molecule, and that's something we can actually observe. So in the next video, we'll start looking at the rest of the second row of the periodic table at their dimers, and in particular, what do we do when we have p orbitals, right? So we've looked at s orbitals so far. We see how they add together, and we'll need to worry about symmetry as we start adding p orbitals together.